A very warm welcome to all of you. I, Akash Sharma, on behalf of MIDAS IT, welcome you all to this webinar series. So, in this slope webinar series, today is the second webinar in which basically I will be dealing with the rock module and a practical application solving one of the design examples. So that is the workflow for today's webinar. First of all, introduction to the rock module. What are the types of failure, like plane and wedge failures? The different modules which can be considered in the rock module, and finally we will be solving the problem on the economical design of slope. So before moving on to the today's webinar, I would just like to summarize what we learned in webinar first. We learned about the importance of the different methods of analysis. If you remember LEM, SRM and SEM, the importance of semi-coupled analysis considering the consolidation and the pore pressure, and the relative ease in using the MIDAS products to simulate the problem. And basically which I showed you the workflow with MIDAS, so that when we'll be dealing with the actual design problem, you will not find any difficulty in finding the options. So first of all, I would talk about the rock module in MIDAS SolidWorks. If you remember, I told you previously that in SolidWorks, we have only the more column as the soil model or the constitutive model. But when it comes to rock, you need different material models to simulate the rock behavior. Only more column is not enough. And secondly, always a plane strain kind of failure is not possible in rock. Many times you have a failure like a wedge failure or toppling failure, which should be considered while considering rocks. So that is why we have a separate module called rock module for stability of rocks. Now, what are the analysis capabilities? When you deal with SolidWorks rock module, you can perform the stereographic analysis, which is basically to find out what kind of failure it is going to take place. And second, you can perform the LEM, that is limit equilibrium analysis, to get the factor of safety for a particular slope. Now, we know that according to the existing discontinuity surface and the combination of the dip direction and the dip of slope, the rock slope failure are classified into the plane failure, the wedge failure and the toppling failure. So these are the various failure modes of rock slope. Now, what is plane failure? Now, it occurs when the dip of slope is greater than that of the discontinuity surface. Now, since it is a case of plane strain problem, as what I discussed previously, the same you can perform. It will be a 2D analysis. Okay. Now the assumptions which is considered here is that the strike of the slip surface and the tension crack plane is identical to that of slope. So 2D analysis is required, and both side faces of the failure block are relaxation phase and no resisting force acts on them. So actually what we do is that we perform a 2D analysis for plane failure surfaces or plane failure planes. Now second is the wedge failure. Now it occurs when the discontinuity in the two different directions intersect. Okay. Now geometry, shape and forces should be considered, and hence 3D analysis become must. So this point is important, that for such kind of thing you need a 3D analysis. Now as you know that SolidWorks is a 2D software, but the rock module is incorporated to deal with the wedge failure, that is a 3D kind of analysis can be performed. Now the conditions which are required is the failure occur when the driving forces that slides down is greater than the shear strength of the joint plane, and the plunge of intersection of two discontinuity surfaces should be smaller than the dip of slope. Okay. So the stability analysis, now when we deal with it, it's very simple. Like LEM, the factor of safety is calculated as the resisting force upon the driving force. So you can see that it is nothing but the shear strength of the failure surface divided by the driving force, which is as a result of the self weight coming onto that particular surface. So what are the advantages? The rock module considers the basic shape. It considers the variation in the slope shape and the various bend shapes. The variety of loads like static, seismic load, water pressure load, and external loads can be considered, which I will be taking in detail. Various reinforcement like rock bolt and rock anchor could be considered. Now, why we actually needed the rock module was because only Moore column was not sufficient to model the various type of rocks. For example, in this we have the Moore column, the Barton bandage, which as you can see the equation on which it is considered. Then you have the Hawk Brown type of material model, and then you have the generalized Hawk Brown, and then you have the power curve. So these are the various types of the material models which are available with SolidWorks. Moving on, now whenever we deal with rocks, it is very difficult to accurately determine the mechanical behavior of the rock joint plane with one material model. The rock module provides with additional option as roughness, and because as the roughness of the joint plane increases, the shear strength and the factor of safety also increases. So this is how it is considered, where tau r is the shear strength of the roughness, sigma n is the vertical stress or the normal stress, and tan phi r being the friction angle of the roughness. Similarly, you can consider the filling materials, like most of the filling materials are sand, silt, and clay, which obviously reduce the shear strength of the joint plane. So the thickness and the strength characteristic of filling material decide the stability of the rock slope. So that filling and the roughness can also be considered in the rock module slope stability analysis. So you can consider the water pressure. Now whenever the water pressure is there between a plane, so there are different options like linear distribution, triangular distribution, uniform distribution, or tension crack criteria, all depending on what kind of opening is there. For example, if the water enters and it is allowed to come out from the next exit, there will be a different kind of variation. And similarly, if the water enters and it is not allowed to come out of the plane, then there will be a different kind of variation. So this kind of variation could also be considered. Then you can perform a static seismic analysis, which is nothing but static load converted from the dynamic load that occurs. So you can consider that, considering the KH value. Now I'll basically demonstrate you with the rock module a simple demonstration on how exactly it works. So this is the rock module in SolidWorks. Just open a new project. I'm just selecting the LEM. Okay, I will just look into it. What is, there's some the software. So what I will do is that I'll just move on to the next part. Okay, so now I'll take the problem on the economical design of slope. If you remember in the previous time when I took the first webinar, I said that this will be the problem statement for today's webinar. A slope is to be designed on a weathered rock, and using landfill here, but to use some waste soil, a 1 meter stretch of the waste soil was used. Now, looking into the environment aspect, the designer agrees to use this waste soil. As you can see, that bottom layer is the rock, and you have waste soil in between, and the top layer is the landfill layer. So now we need to design. Sorry. Now we need to design this using nails to strengthen the slope to obtain a factor of safety of 1.75. Now we need to go for the most economic design of slope without compromising on the factor of safety, which is given to us as 1.75. Fine. Now, always remember that whenever we deal with such problems, the first stage is always the initial stage of analysis, where we have to do actually just the basic analysis without any type of reinforcement. We'll not be reinforcing uh, our model. We'll directly start with the analysis. Let's see that what is the actual factor of safety with that particular arrangement of soil. So this stage will help us get the critical surface. Now, knowing the critical surface, we can identify the area which needs to be reinforced and the minimum length of reinforcement, because the length of reinforcement should at least cover that critical surface area, so the effectiveness of reinforcement increases. Okay, so I'll just open SoilWorks. Okay. So I will say file, import, and import the CAD file, the DXF file. So I'll just change it to DXF and say open. Okay. So this is my geometry for today's model. This is a simple line geometry, and the previous webinar I already have shown you that you can directly use the coordinates to create the model. Okay. Now what I'll be doing is that I will just import the database, which is the soil material property, from already created model file. So this is also one advantage. If you have already defined a model file for a particular model, you can just select that model and directly import the material properties to your model. So I'll go to limiting the variant method, the ground material property. So these are my three layers. You can say landfill layer with a cohesion value of 10, 5, 20. Base materials with cohesion of 5 and internal friction angle of 10. And then you have the weather drop with cohesion 10 and the internal friction angle of 27.5. Okay. So in the first stage, we just need to do the preliminary analysis. That is, we'll not consider any kind of nail. We'll just check that what exactly is the factor of safety for our model. Okay. So just say go to geometry, say smart surface. So the surface is created. If you remember the workflow, then the properties, whatever you have defined comes in here. So we are not going to use nails in the first case. So just select that particular layer, just drag and drop the property. So with the drop, this is the 1 meter stretch of the waste material. Select, just drag and drop. Then you have the top layer, which is the landfill layer. Just select and let's say drag and drop to assign the material properties. Okay. Now having defined the material properties, the next step is next step is meshing, because the method which we are going to use is the SRM, that is the strength reduction method. Okay. So just go to model, just go to smart mesh, select, let's say very fine mesh, generate half the elements, generate the triangular elements, and just say okay. The program will automatically mesh the model for you. Okay. Then we need to provide the boundary conditions. So the workflow is very simple. Just you need to import the model or create the line geometry, create the surface, define the material property, assign this material property to the surface, then mesh it, provide the boundary conditions. So I'll just go to smart support. So just say GS for ground support and just say OK. Okay. Then we have completed the model. Okay. Just go to analysis and design. Say analysis case, add. So strength reduction method, fine, SRM. use all met sets, all boundary sets, and all load sets. Say OK. Close it, and you can just say analysis, analysis, and report. So perform the analysis. You can save the model, and it will perform the analysis for you. So this is very the approach. The first stage should be like we just need to understand that what exactly will be the factor of safety without any kind of reinforcement. Okay. So I will just open a already analyzed file so that we can see the results what we are getting. So this is already analyzed file. So you can see that we are obtaining a factor of safety of 1.21. So in our problem statement, we need to increase it to 1.75. So let us see. So you can see that it is the maximum shear or plane strain for the model. So you can see that this is my critical surface. Okay, the colored zone is the area having the maximum shear strain. So based on this, I have to determine that what is the length of my nails. Also, for example, let us see what other results we get. For example, when we see the displacement, the horizontal displacement will give an idea of what exactly my critical surface is. So you can see that it is very much similar to what my maximum shear strain was showing me. Okay. Then you have the vertical displacement, the total displacement. So now, based on this, as I already showed you in the presentation, that the first analysis helps you with nothing, but it gives you an idea that where exactly your model is failing, okay, and what is the length of the reinforcement you can consider, okay, and which area need to be more densely. For example, in this particular, you can see that the red area is displacing more than the rest. So you can increase the intensity or the number of nails over here rather than going in the top of the nails. Okay. So having during the initial stage of analysis, the next step is the second stage analysis is basically what kind of reinforcement you are going to consider. Whether you are going for a rip wrap, whether you are going for geogrid, whether you are going for nails, okay, or whether you are considering some kind of other reinforcement for your model, then it is the time when you decide the type of reinforcement. And now based on the critical surface area, for example, if you have selected nails, you have to determine the length and the area which is to be reinforced. Okay. So this stage will help you understand the effectiveness of your type of reinforcement and hence help you in coming with the economical design. For example, for the same model, you can select rip wrap, you can select nail, and you can see that which of the reinforcement is coming more effective for your problem. Okay, so I will just open SolidWorks once again. So now I know that what is my critical area or which area I need to start with reinforcing so that I can reach the factor of safety of 1.75. Now, as you already have seen that the factor of safety was 1.2. So I will say file, once again import the CAD file. So I will say DXF. I'm just importing the file. Now I'm knowing that which area, I'm just taking some arbitrary nail values. So I'll just create the nails here itself. I'm saying just 9. So I'm knowing that what is my length. I'm just giving 2-3 nails just to show you that how you started. So this area was more critical. So I will provide 2 nails for this particular area. So I'm just giving 3 names just to show you that how what should be the workflow. Okay. So once again, go to SolidWorks icon, say import database from another file. Okay. So I'm just selecting the files which I have already created. So this many times, and because you need not create or you need not define the ground material properties each and every time. So just say import data. Okay. So once again, you need to remember that next step is to define the smart surface. So before defining the smart surface, first of all, just assign the reinforcement. Because what exactly happens, I will show you. Let's suppose I am not assigning the structural property to the reinforcement first, and I'm just saying geometry smart surface. So you can see that there are a lot of surfaces created, which is not my requirement. But then I have to select this surface, and then I have to assign. So I'll just say Control Z undo. So what is the effectiveness is that you just first select the curves, assign the structural property. So just drag and drop. So these are my names. Okay. Then you just say geometry, just say smart surface. The surfaces are created. Okay. Now you can select each surface. You can see now there is no issue of 2-3 surfaces. It has just considered one surface called one profile layer and not considering the intersection due to the nails which were curves. Okay. So just select it. Just select the weather drop, drag and drop. Then select the waste material, drag and drop. Then select the landfill layer, drag and drop to assign the material properties. Okay. Next, we just go to, we need to mesh the model. So we'll go to model, say smart mesh, say verify mesh, generate higher element, generate the triangular elements, and just say OK. Now you can see that whatever mesh set you have created, you have landfill layer, you have the weather drop, waste material, and the embedded truss. The embedded truss are basically nothing but nails. Now, why we selected embedded truss? Because when I will go to limit equilibrium method, I will go to structural property. If you see that I have selected the element type as truss, I could have selected beam, truss, embedded truss, and I could have defined any type of section for my model. Now, why I selected, now you can see there is truss and you have embedded truss. So what is the difference is that, first of all, while dealing with nails, it is capable of only taking axial forces. So no bending or shear force, so, we cannot consider beam. So it is only the truss which is capable of or which shows a behavior where it only takes into consideration the axial forces. So we select truss. Now why embedded truss? The effectiveness of embedded truss is that when you go with embedded truss, you need not take care of the nodal connectivity. It is so programmed that it will automatically consider the nodal connectivity with the soil mass. So one big issue is removed. So that is why I have selected embedded truss, not truss. Okay. So this is my embedded truss. So what is my horizontal direction facing in the Z direction? So what is my section data and what is my material properties which I have used. Okay, so you can input it and change it accordingly. Next is defining the boundary conditions. So you just go to limit equilibrium method, loads and boundaries. You say smart support, you just say GS standing for ground support and just say OK. Okay. Now, in the previous webinar also I have shown it. Now, once again, I would just like to show one more thing. Now, if you have a varying water level, for example, I will just show you. For example, I am considering that this is my water level, which is varying. Just for an example, so I will just define that water level. I will say OK. Fine. Now, when I generate the analysis case, I just go to analysis case, I add. So this is my first trial. Okay, use all mesh sets. Now I'm using the embedded truss, all boundary sets and all loop sets, and the analysis control data. Now if my water level is horizontal, I can directly input the value. But if my water level is varying, I can just select the function which I have used. Okay. Now since I have not used any water level in my initial stage, I'm not using it here. So just saying OK, and I'm just generating the analysis. So I will say analysis, analysis and report. Perform analysis, just say, let's say. So this is how it will work. Now I will get the factor of safety. So let us see what exactly we get for the first trial. What I will be doing is that I will be just using a already analyzed file. Okay. So this is my first trial. I just selected 3 nails and let us see what factor of safety I am getting for this. So as you can see, I'm directly getting a factor of safety of 2.35 with only 3 nails, and that is also at very different locations. Okay. Now let us see the displacement. So this is the horizontal displacement for me. Okay. The vertical displacement and is the total displacement. Now let us see that which area is having the maximum shear. Okay. So I'll just go to the strings. Okay. And then you can find the option called the maximum shear strain. So you can see that earlier it was a well-defined plane. Now it is not there. So it has increased the factor of safety to 2.35. Okay. Now I would like to show you the various post-processing commands which works for SolidWorks so that you can make use of it. So when you go to results, you have different options. For example, first option which you can see is to see the deformed shape. Okay, let us see the deformed shape. I'm just saying it to be displacement. I'm saying it to be, I just click on horizontal displacement to change this to displacement. I'm just saying deform shape for this model, and I'm just saying apply immediately. So you can see that how exactly it is deforming after application of nails. So I'll just say undeformed shape now. So one option is that. Now the second option is these are basically the view option, whether you want to contour, vector, plot, or you want band or grid. For example, if I say band, you can see the contours in a banded form. Then you have edge, no edge. So these are basically all the various viewing options. The important option comes right from here. So first option is extract result. Now, extract result is basically most effective with the construction state analysis. Okay. So with construction state analysis, for example, horizontal displacement. So if I have 2-3 steps, since we have only one step, so you can select any number of nodes or at the various nodes in which you want to extract the results. I'm just selecting, and you can see the node number here. You can directly say table. So it will give you a format in which you can directly export it to Excel or export it to graph. So for example, if you are doing a pile load test kind of thing where you need with each stage what is the displacement, this will be very much effective. Also, let's suppose I directly want to see what is the maximum value. I will say select maximum value and I will say table. So it will give me the maximum value at the time of failure for my model. Okay. So the first option is the extract option. Okay. Then the second option is probe. The probe is directly, if you click on the model, it will directly give you the value of displacement or whatever parameters which you have selected, horizontal or the vertical or the total, it will change accordingly. Okay. And also if you want to see directly where is the maximum value or the minimum value which is coming in the model, you can directly use the probe function. The next function is the on-curve diagram. So if you want to see like the variation along 2 points, so you can just create the on-curve diagram, right? And just say OK. So when you click on various parameters, it will show you exactly how the variation for that particular parameter is taking place, whether it's horizontal displacement, so how it is varying, if it's vertical displacement, how it is varying, if it's total displacement, how it is varying. Right? So this is the on-curve diagram option. And then finally you have the result calculation, or a function which will help you customize the results. For example, I'm creating a set A, okay? The analysis case is first step. The step is the strength reduction method. So I'm just saying, for example, I'm interested in horizontal displacement and want vertical displacement, and I just want to add a function, let's say A plus B, which is nothing but the total displacement. I want to say OK. Now a set will be generated, which what it will be doing is that it will be showing the result calculation as per A plus B for that particular function. So that this is nothing but how the total displacement is going to be. So if you are interested in any particular type of set function like horizontal displacement plus vertical displacement, or any two particular type of stresses, you can generate a result calculation of the same. Now moving on, so this is how you start with. Moving on to the presentation part. Now you need not do anything, but what you will be doing is that the optimization as per your need, which will be based on your design criteria. For example, for the same model, I started with trial 1, where I reinforced with n number of piles with the length of nails as per the critical surface. I obtained a factor of safety of 2.1. Now, since I have to go for an economical design, in the next trial, what I did is that I reduced the number of nails, as a result of which the factor of safety came around 1.8875. Now, while doing the reducing the number of nails, I was very much specific with what the previous results were, or what the initial results were, because I know that the area which is critical for me should be reinforced densely, and the rest of the areas where I just put the nails for the first trial, I can remove that nails without affecting much of my factor of safety. And the trial 3, I just reduced the length of nail, because initially I know the critical surface, so I went too deep to cover that critical surface, but then I reduced the length of nails, and finally I was able to obtain a factor of safety of 1.76. Okay. So this is how one approach based on the problem statement we have. So if you have any queries, you can write in the question tab box regarding today's webinar. So there was some problem with the rock module demonstration part. So what I will be doing is that I will be attaching a video on the same, so that there was some technical difficulty with the rock module. So I'll just send you a video attached with the link for today's webinar. So with this, I will thank you all to join this webinar series on slope stability. Now, if you have any query, you can directly ask in the question tab box. So thank you very much for attending this webinar series.